Hi guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, we're going to look at the internal energy of a monoatomic ideal gas. And this basically for us to describe this particular aspect of energy, we're going to consider some ideas that we have already done in our previous videos. And this basically is the concept of a molecular partition function, a translation, a partition function, and other aspects. Now, in this case, I've talked about the concept of a molecular partition function, and this, of course, is going to provide for us a general overview of how we can describe a molecule of an ideal gas in terms of an energy. In that specific case, I said that we can describe the molecular partition function of an ideal gas in terms of different types of motion of a molecule. And I mentioned that basically, if we consider a molecule in this case, we're going to describe a molecular state of energy in terms of the translation aspect, as such, or a translation type of motion, the rotation type of motion, and then we talk about the vibration aspect, and then of course we had mentioned lastly on the electronic state of that specific molecule. So in this case, we had represented these four specific aspects of all types of motion using those initials, and I said that we had considered in us representing the concept of a molecular partition function. We had represented these various aspects of energy in terms of a product, whereby we had the total partition function of a molecule represented in terms of the various components of translation and rotation, vibration, and then electronic given as such. So these ones we have given them in terms of products, and therefore we're going to see that for us to consider the case of that is different from a molecular partition function, we're going to look at a monoatomic ideal gas in that specific perspective. Now this is going to have a specific effect whereby we're going to see that for monoatomic ideal gas, the only form of motion that is going to be exhibited in this specific case is going to be the translation component, which we are going to give as QT. And of course, from our various discussions, I'm going to look at one of the way in which we had represented this translation partition function from last discussion. Now, considering the fact that this specific aspect of an ideal monoatomic gas is going to display the aspect of course, the only one form of motion, which is a translation partition function, and therefore we're going to, as I said, represent it in terms of this translation partition function, and find a representation according to the partition functions of representing this specific aspect of an ideal monoatomic gas. And in this particular discussion, of course, I had mentioned that we're going to consider some aspects like the Max-Born interpretation of the concept of the wave function, whereby Max Born had argued that basically for us to describe the translation partition function of this, we're going to consider the concept of a particle in a box, whereby this element of a wave function represents the probability of finding that particular particle in a box at a specific time. And therefore, we had said that we can also consider the concept of a potential in that specific one-dimension box, whereby we had said that if we consider the case of a box having the length of L given between L is x is equivalent to 0 to that specific x is equivalent to L for two infinite impenetrable walls, we're going to have the potential inside this specific well given as 0. Therefore, from the relationship of the interpretation of Max Born and Erin's Schrödinger's equation, we're going to use Schrödinger's equation in finding the potential inside this specific box, which is going to describe the state of that energy, and therefore that's going to provide for us the clue of describing this specific aspect of internal energy, perhaps in a single or three-dimensional space in that particular case. Now, Erwin Schrödinger came up with the solutions to this specific aspect of this particular particle in a box, whereby he gave us the interpretation for internal energy given in terms of the Schrödinger's equation in a one dimension, of course, infinite square well. So we are given this specific interpretation of the negative square of Planck's constant times the square over over 8 over pi squared m. And then we had said that we're going to use this component of the differential operator, which is basically going to represent the one-dimension aspect of this wave function. And this is going to provide for us the solutions to this specific internal energy that we're going to look after. So the solution to this Schrödinger's equation, as we said, are going to be given in terms of this potential, whereby we say that this basically is going to represent a quantum number and the square of the product over this is a Planck's constant, and all over 8 given us and the square of L, whereby L is representing this one, and this is going to be the mass of that specific particle under consideration, and the nx is the specific quantum number in the x direction of this specific one-dimension box which we had mentioned. Now, solving basically for you, we said that therefore we can represent these molecular partition functions in terms of its various components. But we had said that for one-dimension box, we're going to consider this one given as an exponent over negative b, and then we had given u given as such. And this state of representation, we had said that basically it's going to represent this particular internal energy, which we are going to consider for translation. And therefore, we can have a general case for that specific formula, whereby we're going to have this specific aspect of energy represented in terms of. So we're going to do an expansion of this. So basically, I'm going to do away with this. So we're going to have an expansion of this, and we're going to represent this one in terms of Qt as the summation of nx, whereby we're going to consider this specific one-dimension infinite well, and then we're going to have this one as a negative nx squared h squared all over 8ml squared, and then kbt given in that specific order. So this is going to be a one-dimension, but if you are going to consider that this specific a particle has got the 3 states of 3-dimension for nx, ny, and nz for the 3 quantum numbers, and therefore we can do an approximation by having the cube of that one, considering that each of these specific components is going to have an energy contribution that is equal, and this is going to be given as a cube in case we are going to consider a 3-dimension box given as such. And from this specific discussion, then therefore we add an interpretation, whereby we said that basically in finding this translational energy, they are going to be expressed in a close manner, in that we can be able to convert them or perceive them as continuous variables, and therefore we can represent this specific summation form in terms of an integral for us to enable ourselves do this specific summation in terms of a standard integral. So therefore it calls for us to convert this specific summation sign into terms of an integral, whereby we had this one given for the values of nx ranging between 1 and positive infinity. We're going to have the representation of the translation partition function given in terms of this specific summation between 0 and, so basically it's between 1 to positive infinity for the ranges of these quantum numbers. But we're going to do an integration between 0 and positive infinity, and this is going to be given as negative. This is specific representation from the particular value of u according to the Schrödinger's equation, or the solution of the Schrödinger's equation, and this is going to be given as such. So in this case, we're going to consider this one an integral of d in respect to nx given as such. And of course, we had said that this is going to be considered for the 3-dimension of x, y, and z in that specific order. So using the concept of this standard integral for finding the summation, or rather for finding the partition function, we're going to see that this specific integral is going to lead into a form that can be given in this specific case as the translation partition function is equivalent to 2 pi m kbt all over this specific value is basically the Planck's constant, all over the square of the Planck's constant, and then we're going to have this one raised to power 3 over 2, and then v. So this basically is the result of the integral from applying this standard integral from this specific case for the integral instead of a summation. And of course, as stated, we have taken this specific procedure to enable us use a standard integral and trying to evaluate the result for this. Now, this element of v, which I've given in this case, this represents a volume that we're going to find by multiplying these three components of the three range of integral numbers for the x, y, and z for n. And then therefore this is going to be given in terms of the cube over L, which is going to be representing our volume. Now in this case, from this derivation of the particular formula, the result we have obtained for the translational partition function, we're going to have another, of course, a definition we're going to obtain from this, which is going to be given in terms of this is the de Broglie's wavelength, which is given in terms of the square of the Planck's constant 2 pi m kb t given as such, and this is going to be raised to a half. So in this case, if we try to look at our specific results for this particular integration, it's going to have a component of this a particular de Broglie's wavelength, and therefore we can reduce this specific result and give it in terms of course, a factor of the de Broglie's wavelength, and therefore our q t is going to be given in terms. So this basically is going to be in this specific expression, it's going to be an inverse or a 1 over sine of which is going to be an inverse over the lambda, and therefore this is going to give us an equation of the form of lambda negative 3v given as such. So this is going to reduce into a translation partition function given in terms of qt is equivalent to lambda to power 3v, and that is going to give us the translation partition function for that specific type of representation for the translation partition function. Now, if you consider the case of a monoatomic ideal gas, which we have mentioned, basically said that we can describe this specific monoatomic gas consisting of n number of atoms in terms of atomic translation partition function. And of course, this is going to be given in this specific order, whereby we are going to have a monoatomic ideal gas described in terms of atomic translation translational partition function. Now, given two cases for the distinguishable and the indistinguishable particles, and in this case, I said that basically for a gas and liquid which are going to be having particles which are swapping positions, unlike solids which are, of course, at a specific position or lattice, we're going to represent this specific, of course, indistinguishable particles using this specific partition function, which is going to be Qn over n factorial. So for us to represent this specific representation in terms of this, we're going to have this specific q raised to power n given in terms of lambda negative 3n. So I'm going to have this exponent of a factor of n being factored, and this is going to be given in terms of n factorial given as such. So this represents basically the translational partition function for that kind of a gas. And we're going to, of course, see that we can write this one in terms of potential, or rather in terms of internal energy, by considering the definition of internal energy from the partition function, which we have done earlier. So I'm going to use this specific representation, whereby we had U represented as kBt, the square of that, and then we had this partial derivative over Q with respect to temperature at constant volume given as such. And we said that basically from this one we can represent our partition function, which is going to be Q, by doing a replacement of this specific aspect of the equation that we have found for the partition function in this upper part. So we're going to have this one given in terms of U equivalent to kBt, and then this is equivalent to, of course, the integral of, so this substitution basically gives me negative over Vn, and then I'm going to have this one extended as over n factorial, and this is going to be all over with respect to t, and then at constant volume given as such. So this specific equation can be solved by using the laws of logarithms, and we're going to consider factors which are dependent on temperature. Now, from this case, they are given this specific aspect of the de Broglie's wavelength in terms of the square of h given as basically given that one as the square of h given as 2 pi m kbt, and then this one raised to a half. So from this specific aspect, we are going to see that basically the aspect of the de Broglie's wavelength is going to depend on temperature, and therefore trying to reduce this specific formula in terms of or with respect to temperature through the process of logarithms, we are going to obtain the value of kbt, the square of that given in terms of the partial derivative of natural log of t, 3n over 2, and this is going to be over dt given as such. So this basically is an involvement of different laws of logarithms, and they're going to assist us reduce this particular formula into that specific level. So this is going to be under constant volume given as such, and of course this is going to reduce into a version of the formula that's going to be given in terms of u is equals kb, the square of t, and of course we're going to take that specific exponent 3n over 2, and it's going to form that specific part of the coefficient of these components, which are of course into brackets. According to the laws of our logarithms, of course that's going to be appropriate. In case we have a power, then therefore we're going to take, in case we are differentiating for a power in case of having x power m. So this implies we're going to have this m as a coefficient x m minus 1 given as such, and that's basically what I've done in that particular case. So we're going to have this u still being simplified in terms of that one, and of course we're going to consider perhaps taking this specific constant which we have given as a coefficient of 3n over 2, and then we're going to have kbt at the square of that. And this one inside here, having taken this particular constant out for 3n over 2, we're going to have this one given as the natural log of t given as 1 over t. And then we're going to have this one reduced into u is equivalent to 3 over 2 n. So this is going to be n kbt. But there's a relationship that exists between these specific two components of the Boltzmann's constant and the universal gas constant, which are going to be given in terms of so this universal gas constant and Boltzmann constant, they have a relationship in a sense that we're going to have R represented as NAKB. So therefore NAKB component is going to be represented in terms of R. Therefore this reduces the formula of U internal energy of 3 over 2 and then RT given as such. So 3 over 2 RT basically is going to be our molecular translation internal energy, which is going to represent, of course, this a particular value of internal energy that we have obtained from evaluation of this specific gas. Now, this is going to be in agreement from both the classical and the quantum mechanical aspects, in a sense that from the Equipartition theorem that arises from the classical theory, of course, this is going to be having that specific components still having the same value. Now we can consider this one as well to be true since from the Partition Theorem, of course, which states that every degree of freedom should have an energy of a half kBt. So for 3 energies, we're going to see that this one is going to be having 3 components for the denominator, which is going to be, of course, in agreement with this having this specific aspect of 3 over 2 kBt, and that's going to be in agreement with the Equipartition theorem. Now, this basically is how we can represent the internal energy of a monoatomic ideal gas, and of course, we are going to come across this specific formula in different discussions as we go by. So that is it for now, guys. Bye, God bless you. Catch you in our next video.